Welcome everybody in the lecture hall, welcome everybody on Zoom, welcome everybody from the future. Today I'm going to continue what we started yesterday, meaning that we are going to be looking at relational databases and the SQL language. I would like to start with 2 clicker questions to get you in the mood, and then we'll proceed. So let me switch over to this question to make you think a little bit. I'm pretty sure some of you experienced that, or maybe many of you. So when you copy over some files on your laptop, the progress bar typically does not go uniformly from 0% to 100%, right? Pretty sure you observed that. So why is that? Is it because the files have different sizes? Is it because the progress bar doesn't refresh regularly and the transfer is actually always happening uniformly? Or is that not true? Maybe you are lucky enough that your laptop always shows uniform progress bars everywhere. Or is it because of the CPU usage? Now, I hope that we don't have now a network problem with the page. Otherwise, we'll do popular votes. It might be that the servers of the ETH EDU app are overwhelmed at the start of the semester. I will drop them an email to ask them. All right, let's do a popular vote then. Who thinks that it's because the files have different sizes? Raise your hand. Okay. Who thinks that it's actually just with the progress bar implementation and it's actually uniform? Not many. Who thinks, who actually is lucky enough that your progress bar is always uniform? Nobody, right? And the CPU usage? Some of you. Ah, it's 50%, 50%, right? Between CPU and files have different sizes. Well, in fact, it's because of the different sizes. And the reason I'm asking you the question is that it's directly related to what I told you yesterday about capacity, throughput, and latency. Because what's going to happen is that if you are transferring very large files, then maybe you wait a little bit to start, but then while the large file transfers, it's the throughput that constrains everything, right? It's basically the bandwidth of the network or the bandwidth of the disk I/O. But if you instead try to transfer very small files, then because of latency, what's going to happen is that at every file you wait until it starts, then you transfer the file, which is actually quick because the file is small, and then you're waiting again for the next one. So basically, with very small files, the bottleneck is the latency. It's actually going from file to file. With the large files, the bottleneck is the throughput. And this is the reason why the progress bar isn't actually showing uniformly. And this kind of thinking will be very important throughout the semester of understanding this notion of capacity, of throughput and latency. But again, some of you asked yesterday, this idea of batch processing, we're going to come back to it many, many times in different weeks of the semester, in particular during the HDFS and MapReduce weeks. All right. Oh, now it seems that it actually works, so I can show the results. No, doesn't want to. Okay. So now, let's also do a popular vote on this one. How familiar are you with databases and SQL? So who doesn't even know what that is? And it's fine to raise your hand. We're in a university, we're here to learn. Not everybody is a computer scientist. Who never heard of this? Okay. Who heard of it, but that's it. Okay, some of you, and no worries, we are going to go into them. Who already program in SQL for personal websites, know select from where and so on. Okay, a lot of you, yeah. And who is very proficient all the way to the 6th normal form and implements video games with SQL? Oh, we have some, okay. Very, very good. So I write an email to the EDU app team to let them know that there's an issue with the connection. All right, so then I'm switching back to the slides. Proxy error was showing in the browser. Okay, so where were we? Well, we actually did a lot, right? You know who this person is, Edgar Code. And then data independence, right? I don't need to repeat all of the shapes of data, Then I told you about models, which is what are we dealing with and what can we do with it, right? With the analogy with cooking. And then I discussed briefly the ideas of the concepts behind the relational tables, meaning tables, rows, columns, and primary keys, right? And then I told you about this scary mathematical definition as a relational table defined as a relation, which I don't like for various reasons. One example was that in Cartesian products, it's actually numbers to identify the positions and not strings. And another aspect is that it's ordered, but the columns shouldn't be ordered, right? So what I do in order to explain, especially to non-computer scientists in information systems for engineers, is that I explain that in order to have a table, you just have some attributes, and then you have a set of tuples. This is where we stopped last time, but I would like to explain what a tuple is, because a tuple in that sense is not exactly going to be a tuple in that sense right there. In fact, a tuple, mathematically, what we call a tuple when we define it in that way, the fancy term would be a partial function. It basically is a function that associates strings, the attributes, to some values, but partial because it's not associating every possible attribute with that would be trillions or quintillions of them, right? So it's a partial function. So this is an example. This actually corresponds to a row, right? A tuple is the same thing as a row. And this tuple associates PID with 2, last with Ramanujan, first with Srinivasa, and country with India, right? So this is tuple. Another name for that is map or associative array, right? And that I think you're familiar with, especially computer scientists, all right? So of course, database people don't actually represent tuples in this way. They might represent them in this way. Actually, we are going to do this a lot in this lecture. Who knows what this is? What kind of syntax this is? A dictionary, yes, in Python. And the name of the syntax? JSON, exactly. And we are going to include that in our lecture. So you see, a JSON object or dictionary is actually a partial function from strings to values, right? But a lot of database people have something even better for displaying this. They are going to look at it like this, like a table with a single row with the attributes over here and the values in here. Note, and that will keep us busy during the semester. Here we can do it because it's flat, right? But in the case that you have nestedness, we'll study that, then you can no longer do that, right? But if it's flat, then you can actually display it in this way, right? So this is a tuple. For whom is that clear, especially those who didn't have a relational database course? For whom is that clear? Okay. So now we have one tuple and we need to assemble the tuples as tables. It turns out that sometimes we can do this, sometimes we can't. So I'm going to give you an intuition. The first, there's 3 rules that we need to fulfill as a set of tuples to have a relational table. 3 rules. The first one, which I call relational integrity, is that all of the tuples, there's 3 of them in here, must have exactly the same attributes. That's rule number 1. And when that's the case, this is when you can merge them into a single table, right? So you see that's here the set of 3 tuples, and now they are merged in a display, a fancy display of a single table. This is relational integrity. All tuples have the same attributes. This is a counterexample where they don't have the same attributes. For example, the second tuple is missing the name, and the third one is missing the physicist's attributes, and it has an extra country attribute, right? So this is here broken, rule number 1. Okay? Rule number 2 is called atomic integrity, also known as the first normal form. Atomic integrity means that all of the values in the cell of the table, here, these are atomic values. I think to understand what I mean here, it's better to show you a counterexample, which is right here. These are not atomic values. Why? Because here we have nested structures. I have a table in a table. And I like to compare this with the Inception movie. Who saw Inception? A dream in a dream in a dream in a dream. So it's the same thing here, a table in a table in a table in a table. If you have a table in a table in a table in a table, then you are breaking atomic integrity, you are breaking the first normal form, right? So here you only have atomic values. We are going to also cover all the types of atomic values in a few weeks, but it can be strings, dates, numbers, booleans, and so on and so on and so on, right? So this is the first normal form, and this is a counterexample of first normal form. Rule number 3 is domain integrity. Domain integrity says that within each column, all of the values should have the same type. There should exist a type that is instantiable, meaning not abstract for the computer scientist, a type that is instantiable in every column. So here it's the case because these are all strings, these are all strings, these are all Booleans, and these are all integers. So here we check the box for domain integrity. Here we don't. So I didn't even put types in there because we have a problem here is that we have Booleans and integers. Here we have a string and integers and so on. So here we are technically breaking the domain integrity. Then you could tell me, okay, yeah, but we can put everything into a string, right? We can just put string here and make everything a string. In fact, this is exactly what some systems do, but that's not really nice because that pushes the burden back to the user to actually deal with casting the string back to actual types. All right, so here, this is domain integrity, and here it's broken. If I have a set of tuples that checks all the boxes for all 3 rules, relational integrity, atomic integrity, and domain integrity, then I have a relational table. And this is the beautiful world of relational database management systems. This is the beautiful world of SQL with a product like PostgreSQL, MySQL, SQL Server, DB2, and so on and so on. And this is what you learn typically in the bachelor's lectures on relational databases. And of course, we are here to break rules. So in big data, we will happily break these rules. And this is the world of NoSQL. And we are going to break these rules during the entire semester. We're going to have data that doesn't have domain integrity, that doesn't have atomic integrity, that doesn't have relational integrity. Sometimes some of them, but not all, right? We can also selectively break rules, but this is NoSQL. But in this lecture right now, the SQL brush up, I'm going to stick to the rules and show you what happens if we actually do respect all of these rules. So if we do respect all of these rules, and we have a relational table in that sense, then comes the relational algebra. The relational algebra is a beautiful mathematical framework that manipulates tables. It can be compared to mathematics. You can also manipulate integers and real numbers and complex numbers with addition, multiplication, and so on. You can manipulate matrices with multiplication, composition, and so on and so on, right? So tensor products and so on. Well, we can do the same with tables. And in fact, it's beautiful and it's especially beautifully mathematical. So what can you do with tables? I'm going to go through this. You can do the union of 2 tables, so that's set queries. You can filter some information in tables, selection, projection. You can rename some of the attributes or even tables. You can have what I call shuffling queries because the data is just it's a big mess in the data flow, but it's grouping and sorting. I will give you, probably you already have it if you studied the relational database lecture, but especially in big data, we'll see that grouping and sorting is expensive, much more expensive than the others, and joining even more expensive, right? So that's the Cartesian product, natural join, and so on. But let's go through them to make sure. And again, I know I told you, some of you will get bored because you already know that, and some others might be scared because of the speed at which I'm going through this. But let's do this. The first thing you can do is a selection. A selection means you have a criterion. For example, everybody from the United Kingdom, Great Britain, right? So we select these 2, and we get another table that has less tuples, right? It's a subset of the tuples. This is called selection. We can do the same with columns, right? When we do this with columns, we select, for example, the last and first. If we project to the last and first columns, then we get another table with all the tuples, except that we only take last and first. Of course, if you know that a tuple is a partial function, then you know that mathematically you're restricting the partial function to a subset of the domain, right? But here we just keep the visuals. Okay. Another thing that you can do is grouping. Grouping is, for example, if you have a list of all the cities in Switzerland together with the number of inhabitants and the cantons, then you can try to group by canton in order to aggregate the population in every canton. That is grouping. So here is a very simple example with arbitrary values there, and then what we want to aggregate. And you see there's only 3 values here, foobar and foobar. So we have foobar and foobar, and here we aggregate as the sum. And also do it with other things than sum, but here it's the sum of this plus this plus this is here and so on. This is grouping. It's extremely powerful. In fact, that's a very common use case in data analytics. Then you have sorting. And now, if I keep talking about sets of tuples and I'm saying that I sort, I can maybe hear some people scream because no, you cannot sort a set, right? The set doesn't have any order. It's just either you're in a set or you're not in a set, but there is no order. This is why I told you, yes, but we also have bags of tuples or lists of tuples, right? We can change the way we define tables. So if I define a relational table as a list of tuples, then I can sort in this way. And many relational database systems allow you to do this. This is one more reason why I don't like the textbook definition using the relation, defining the table as a relation, because in the relation, you cannot have this list of tuple semantics, right? So this is another reason. Yet another thing you can do this time with 2 tables. If you take 2 tables, then you can do the Cartesian product of these 2 tables. What does that mean? You pick for every row in here, you combine it with every one of these. So here we have this full one combined with every one of the 3, and here combined with every one of the 3. So you see you have 2 on the left and 3 on the right. 2 times 3 gives you 6. So you always get the products of the sizes on the right. Okay, that's a Cartesian product. Now, this you must be careful about because this is big data. So it might be that we have 1 billion tuples on the first table, and we have 1 billion tuples in the second table. If you do the Cartesian product of these 2, you're going to end up with a quintillion tuples in the Cartesian product table. If you're doing that on a cluster, you're going to crash it, right? This is just not going to work. And in fact, it's so dangerous that there is even a flag to deactivate Cartesian products in Spark to make sure that you don't do it. You can still deactivate the flag at your own risk if you know what you're doing. But this is basically very dangerous if you deal with the very large quantities of data. Then you have joins that are less dangerous than Cartesian products because unlike a Cartesian product, in a join, you only combine some of the tuples with some of the tuples. In fact, you take those that match. So in that case, I change slightly so that I have an attribute that has the same name here. So it's a natural join, natural thing to do. And I will only match the 1 here with the 1 there, and the 2 here with the 2 there. So this is called the join. Okay? So far, so good? Who is following? Okay. For whom was that new but still understandable? Okay, good. And don't hesitate to ask questions, and you'll have practical exercises with SQL, and I promise you it's so simple that will really help you a lot understand these things. All right. Now, the next thing I'm going to explain is going to be very scary. So I have to warn you. But I also have to clarify that it's not very important to understand the details of that. The reason is that then I'm going to throw that away. So the reason I'm explaining that is to explain why we are actually not going to respect these things. Normal forms. So why do we have normal forms? Normal forms are kind of best practices for the design of databases. If you don't know about them and you just go ahead and start building tables, you're going to have problems with your website. And the kind of problems you can have is that some data might be duplicated at several places, and then you delete it at one place, but it's still there somewhere else. Or you want to update it, but since it's duplicated, you update it here and you forget to update it in the same way there. Or even worse, you update it in different ways at different places. Or you can also insert things, but forget to insert them somewhere else. So these are called update anomalies, delete anomalies, and insert anomalies. This is why some very smart people came up with best practices and mathematical definitions of constraints that should be put on the tables to avoid these issues. And these constraints are called normal form. And talking about normal forms almost sounds like playing music, because you really have like the first normal form, the second normal form, the third normal form goes all the way to 6, and maybe there are even more of them. But I'm just going to give you an intuition. And again, don't be scared, because that's very quick. Normally, it's something that takes several weeks to actually teach this. So it's really just a very high-level thing. In order to understand normal form, you first need the notion of functional dependency. A functional dependency, there's function in there. It just means that a column could depend on another column or on several other columns. In that case, for example, the name of a lecture obviously depends on the ID of the lecture at ETH, right? If I give you the code of the lecture, so 263 blah, blah, blah is the big data code, then you know it's big data, right? So you notice the functional dependency. If it's the same code, then it has to be the same lecture name, right? So there is a functional dependency from this column to this column. That's the first concept to be aware of. And generally, if you have too many functional dependencies, this is where this trouble arises. For example, if somebody wants to update here a lecture code and they forget to update the lecture name, then they have a problem. That's why this is a bit dangerous, the functional dependencies. Okay. Now, there are cases where you're lucky enough that a couple of the columns have enough information to fully identify the whole record. In that case, for example, if you know the leggy, the name, and the lecture ID, if I tell you, for example, 30 blah, 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 Alan Turing and 263, then you know that you are on this row. This is what a super key means. It means there's a functional dependency from these three attributes to everything. This is a super key. Now, super key could have useless attributes. For example, if I take all the attributes of the table, then it's a super key, right? If you know all the attributes, then you know all the attributes, right? So based on a super key, you may want to remove useless attributes. For example, if you notice that the name depends on the leggy, right? Your leggy number identifies you, right? So that identifies the students. So technically, the name here is superfluous in my super key. I don't need the name. All I need is the leggy and lecture ID, right? So I can try to find minimal super keys. When you have a minimal super key, that's a candidate key for the table. And in fact, this is what I called primary key earlier, right? The reason it's called candidate key is that you might have several candidate keys and you make a choice. You prefer one of them, and this is one that you are going to say, this is my primary key, right? So now if you know the leggy and the lecture ID, then you know where you are, on which row you are. For example, if I tell you 25 as the leggy and 1, 2, 3 on the lecture ID, then you can tell me this is where you are. So this is a candidate key, minimal super key. Then this is another one, just to show you there can be several of them, and this is why you can pick as a primary key whichever you want. Now, if you try to find all of the candidate keys, and you look at the attributes that you've used, you might notice that some of them are just left alone. This one, for example, is not going to be in any candidate key, right? This is called the non-prime attributes. So now coming to the normal forms. The first normal form, that's easy, you already know it, that's the atomic integrity. The first normal form says you cannot have a table in a table in a table in a table, right? First normal form is atomic integrity. This is here broken, that's a counterexample, and now that's the first normal form. And then it goes up and up and up and up, second, third, and so on. So we keep restricting, 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 right? I'm putting constraints on my tables. The second normal form puts a constraint here saying, I forbid a kind of functional dependency. So what I forbid here is that I don't want for something to be dependent on a subset, a proper subset of a candidate key. I don't want a non-prime attribute to be dependent on that. The details here are not important. You don't need to know that by heart. The only thing you need to understand is that I keep restricting more and more and more and more when I go up the normal forms. So that's a counterexample here. You remember that this is the candidate key, these two together. But here I have a functional dependency between part of it, half of it here, going there to this non-prime attribute, the one that was left alone. This is not good. I don't like that. For the second normal form, I don't want to have this. So this is forbidden in the second normal form. And yeah, that's pretty much it. So here it's in the first normal form, but it's not in the second normal form. And then I keep restricting even more, right? So if I'm less than a candidate key, then I cannot be a super key, right? So in the third normal form, we go even one step further and say, we forbid any functional dependency going from something that's not a superkey to a non-prime attribute, right? So it's more restrictive than the second normal form. And here you have an example here where it's broken. And then I continue to restrict more and more and more and more. So here I was saying, okay, not a superkey to non-prime, it's forbidden. Now I'm restricting more by saying not a superkey to anything is forbidden. So you see it's getting stricter and stricter and stricter, what I'm restricting. And here is an example where it's broken. So now, again, you don't need, if you didn't see that before, it's absolutely not important that you remember these things or even understand these things. Just know that the rules keep getting stricter and stricter and stricter as you go up the normal forms. Now, what do we do about it? Because it's nice to know that we are breaking rules and breaking normal forms, right? What does that give us to know that I'm breaking rules with a table? Well, what's really nice is that the normal forms, the people who designed the normal forms also gave us algorithms to transform the tables in such a way that they would respect the rules. This is what you get. So if you take this table here that breaks the rules, you can cut it into multiple tables. And if you join them back together, you get back what you have here. That's the join. That's why the join is important. So here's the one thing you need to remember about normal forms. Typically, a higher normal form means that you're going to spread the data over multiple tables, and each table does one thing and does it right. For example, I have a table of students over there. I have a table of cities over there. I have a table of lectures over there, and I have a table that links my lectures to my students. This is super nice. That's beautiful. This is exactly, I'm pretty sure ETH does it like this and doesn't do it like this, I'm pretty sure. Because we stick to the normal forms that tell us how to design the database. This is bad, this is good. Which brings me to, we are now going to throw all of that away. Why? Because we're dealing with large scales, and that actually makes things more complicated. So in this course, it might come as a shock because some of you spent several months studying these things. Now we are throwing that away to the point that we might only be in the first normal form, or we might even see tables in tables, right? So very scary. So that's it. We're going to break these rules. And the reason why I'm telling you that going to a higher normal forms means splitting the table is that the reason we are doing this is we're just analyzing data. We are not writing data, we are just analyzing it. So if you analyze the data, you don't care about these update anomalies, insertion anomalies, and so on. You don't care about these things. So if I'm working with data that is in high normal form like this, I'm going to have to join these tables. So imagine these tables, they have millions of rows each, and I have to join them. This is very expensive. So in a way, if I throw away the normal form and instead store it like this, I don't need to do any join. It's already done here. I already have my join table, right? So this is why for big data analytics, I love to have data like this, right? And less like this because I have to do joins, right? So again, this is the lesson to remember. Joins are very expensive, which is why we throw away normal forms and typically have a big table that breaks rules, but that's okay because we want to do data analytics, right? And so we'll see plenty of the examples like this in the coming weeks, right? So now you know why I told you don't worry about understanding normal forms just because we're throwing them away anyway. Okay, now there is this language, SQL, that is a declarative language and that allows you to query relational tables. SQL is really, really, really nice. It's nice because it's easy to learn. You don't even need to be a computer scientist to learn SQL. It's much easier to learn than, let's say, Java or Python or C++. And it's part of this whole ecosystem of languages, right? So you have assembly code and then languages that are higher level. Then you have these frameworks and APIs that are lower level. And you have the query languages that make it more convenient. And this is the machine learning part. I just had to put buzzwords in here, where we have these frameworks as well. And slowly, it's slowly happening. We're not quite there yet. We will get languages on the high level that replace these complicated frameworks, right? So SQL was born actually at IBM from Don Chamberlain and Raymond Boyce as an early prototype in the 70s. It's already 50 years old. So it was in San Jose in California, in the now as Almaden, the laboratory. And it was called System R, and initially SQL, S-E-Q-U-E-L, it means Structured English Query Language. And that was actually sold. They were making money with that. And the first customer was Pratt & Whitney, which still exists today in 1977. But they went into a trademark war on the SQL because some other people didn't agree it was called that way. So this is why they changed it to SQL. But this is the reason why many people still say SQL, including me. So you might have heard of Oracle, but actually it was called for Software Development Laboratories in 77, then renamed to Relational Software, and then became Oracle in 82. That was the first commercially available product, inspired by System R. All right, it's declarative. Why? Because you don't have to explain how you implement the query, right? So the best way to understand declarative and functional is that declarative is like you go to the Mensa and you say, I'd like the veggie menu, right? This is declarative. Imperative, like C++, Java, Python, means that you have to cook yourself. You take the recipe book and it tells you exactly what to do, right? So that's kind of the difference. So programming in SQL, you don't need to worry about the details of implementation. You just need to say, I want a selection, a projection, a join, and the system is just going to take care of it for you. Set-based means you can manipulate millions or billions of rows at the same time. Right? It's just a fancy word for this. That I already told you, SQL, SQL, it doesn't really matter. I tend to say SQL because I've been in contact with a lot of people who say SQL, but you can say both. Just know that it's exactly the same thing. Who here would say SQL? Who would say SQL? Okay, we'll do the same thing at the end of the semester and see if there was an increase of SQL. Okay. So declarative means we have a logical model separate from the execution. We already heard that. That's data independence, right? This is data independence here. So it's the idea that I have these things I showed you, the join, the selection, the projection, and so on. So if I give you a table, let's say as an array of dictionaries in Python, and I ask you to implement a selection or a projection or a join, then you might spend 1 hour or 2 hours writing some code that does that. Maybe 1,000 other people in the world are going to do the same thing. Why do we do it 1,000 times? We can just ask one person who is a specialist in that to do it just once, give you a library, and then you just go ahead and say, I want to select and project. And in fact, if you have millions or billions of values in there, then having that implemented by an expert is actually make you more performance than if you had to do it yourself, right? So this is one of the benefits of having this, this separation between the logical model and the physical execution. Plus, we can parallelize without changing the upper layer, and we are actually going to do this in this lecture. SQL is not only declarative, it's also functional. Functional is just like a Lego game. It means that you can put an expression in an expression in an expression in an expression. It's again like Inception, right? So let me show you SQL. A lot of you know it, a lot of you don't, but we are going to have a lot of exercises next week that will be released to you, and you can just type your SQL queries and learn it. But I just want to show you a little bit what it looks like. And I hope that you will also find it quite simple. So the select from where is kind of the part that many people heard of in SQL. So here, I am doing a selection. It means that I'm restricting to last name equals Crusher, and I only want to keep the rows where the last name is Crusher. So these are Star Trek characters, right? So if you look at the last name, only this one is actually Crusher. So you select and only keep that row right here, right? This is what this query does. Persons is the name of the table, right? You always give a name to the table. And the star here means you take all columns, right? Select star. This here is a selection. if you had to do it in C++ or Python without a library, you would probably use a for loop with an if inside. But again, that would be more cumbersome than just writing this. Projecting query, instead of the star, I'm putting the columns I want, first name, birth date. I don't even put a where clause in there. I'm keeping all the rows. And that means that I'm just keeping this one and this one. That's what I get, right? Just a projection. Be careful because that's I have no idea why that is, but the projection happens in the select clause and the selection happens in the where clause. So I don't know why, but this is how it is. All right. Then we can rename columns using the as keyword. So I can say the first name now, I prefer to call it who, and birth date, I prefer to call it when. And you see that changed the name of the columns right there. Order by, it means that we have a list of tuple semantics. And actually most of the relational database management systems do have list semantics. So if I say order by birth date, it's going to reorder the tuples, reorder the rows. And now you see it's actually ascending by default. Group by also exists. So here I have all of these people and I want to sort them by century, right? I want to know how many people are from the 23rd century, which is the original series, and 24th century, which is the next generation, right? So here I see 2 people from the 23rd century and 2 people from the 24th century. This is a group by. I let you imagine how much time you would spend on this if I just asked you to do it in C++ or Python, right? This would take a lot of time, except if you use a library. But again, if you use a library, that's pretty much the spirit of it, that somebody else did it. So with this, with SQL, you just write your query, 3 lines, and you can rely on the experts that actually implemented PostgreSQL or whichever system and already once and for all wrote an implementation of the group by. Right? So this, do we have a question over there? Maybe we can, maybe not throw it, but maybe with little hops. Yeah, small hops, we want to be careful.
So you said that SQL is a declarative language and a functional language, and I would like to know what exactly is a query language and what is a query? What's the definition of that?
Mm-hmm. It's also a query language. So I would say that this is orthogonal. A query language says something about the purpose of the language. Why do we have the language? And the purpose of SQL is to query data. So that's the reason it's called a query language. Saying that it's declarative or functional is not something about the purpose of the language, but it's a property of the language itself in the way that it is designed. And the link between the two is that, as a general wisdom that many database researchers will agree with, it is best for a query language, so a language whose purpose it is to query data, it is best if a query language is declarative and functional. That is one of the lessons from the past 50 years. And why? That's data independence, the reason. Does it make sense?
Yeah, it does. So a query language is basically a language that is only there to query data. So for example, if I would use Python libraries to query data, it would not be a query language, of course, because Python can do more than that.
Exactly. Python is a programming language. It can do much, much more than just querying data. You can also create, for example, you can create pie charts with some libraries and so on. So it can do much, much more than querying data. So a query language means that it has a very narrow scope, right? It's only there to query data and nothing else.
Thank you so much.
Yeah, thank you. All right. Now, let me show you more of SQL. We also have having clauses. Having is a little bit like where, in fact, like this, but it's after the group by. So that's the reason why it has a different name. So what we mean here is we group by century, but we only keep the centuries where the count is more than 2, right? So in that case, I put on purpose 3 from the 24th century and 1 from the 23rd. And since I say group by century having counts greater than 2, then I only keep the 24th century in there, right? Oh, I could put a where, but it would have to be before the group by. but if I put it before the group by, I don't know yet how many there are. So that's why I cannot put it before. Why it's called having, that I don't know. It's a design choice. And we will see in the other language, JSONic, having is actually also called where. So you will also see a language where it would be group by and then where after that. Yeah. What you need to understand is that it has to be after the group by, because we only know the counts for the groups once we have groups, right? That's the reason. Okay. Now here's the whole set of clauses. This is just so you know, it is exactly in that order, so that you can almost learn by heart. Select from where, group by, having, order by, limit, offset. Limit offset is just to paginate, to say I want the first 10, the next 10, the next 10, just like Google results, right? Okay, learn that by heart. Select from where, group by, having, order by, limit, offset. Many are optional, you don't need all of them, but it has to be in this order. If you try to swap them, it will not work, right? The order is important. If you learn that by heart, you will already be capable of doing many, many, many different queries using SQL, right? Next week, I will continue and finish this with some more queries, but let's stop on that, the learning that by heart, and then next week you'll have the exercises. I would like to check just before you leave, and again, hoping that this time is going to work. Oh no, it didn't copy it. So I usually will do at the end of every lecture a check of whether you understood what I told you. So let me do it quickly. Who understood everything I've been telling you today? Wow, I'm impressed. Okay, that's awesome. It will not happen every week, right? Who understood more than 80%? Okay, more than 50%, but less than 80%. And less than half. Okay, this is good. This looks good. If you didn't understand some of the things, ask us questions. Don't hesitate to write to us. Ask questions on the Moodle Overflow, and we will answer. Thank you very much, everybody. You can come to me for questions offline. Thank you very much, and see you next week in E7 again. Goodbye.